Right, so yesterday we left you on this question here, calculating the reactions using a moment release. So if you recall, the standard process is to put a release at that position there so that each span then becomes a simply supported beam. So putting a hinge or a pin at each internal support so that that one becomes a simply supported beam and that one becomes a simply supported beam. Now, just a question. When we are calculating the angles, where work is done, I suppose, or the difference between the two. Remember that this one started out straight. So so that before you put in the hinge or the moment release, there would be one gradient at that point. So that concept should be pretty clear from what we've studied before. If you remember this case here, which we did earlier, where we forced a rotation at that point there. So before that was completely straight, and then we forced a rotation there. So if you continue the completely straight line, then you can see that the rotation is that. Okay, so that would be the rotation. That would be the rotation at that point. So I think that question came up in Piazza last night, and you can probably see when we're calculating the rotations. Remember, we're calculating the rotations on both sides. So for example, if it had been a beam like that, and we had done that in terms of the rotations, then that would have been a straight line before, and then it's that angle that we're calculating, not this angle and not this angle. But in this case, in the case of the previous one, it would have been, well, here it would have been twice the value of each side that the rotation is going through. So let's continue, and at this point here I keep on stressing I don't really care which way I'm putting my moment, and the same would go for the virtual one, because I would be convinced at the end that I have a hogging bending moment there. So I'm just going through these calculations just to work out the numbers, and I'm not relying on the sign that I get at the end to tell me whether this is hogging or sagging. So I've already decided before I started the question that this one was going to be a hogging bending moment, and I'm now just working out the magnitude, which would just be x multiplied by delta 1 naught and delta 1 1. So this is what I would call the flexibility statement. Okay. So we'll talk a bit later on as to why we've got this notation here, and when we do that, you know, you can probably see how this can be expanded to multi-span problems, almost as many spans as you want, and then you can get a matrix that you can put into Microsoft Excel and then do the inversion and then calculate all the reactions from there. Anyway, for now, we've just got delta 1 naught, and we've also got the delta 1 1, which I would say is the change in both angles, or each side added together. So let's continue. So we'll move on to step 2. So I separate it into step 1 and step 2, just to avoid any confusion as to where virtual work comes in. Virtual work is just a method to calculate the deflections. So use virtual work unit load method, and in this case here to calculate rotations, since in this case here delta 1 naught and delta 1 1 are rotations in radians. So let's start by calculating that one there. So I'll just stick the modulus sign in. I should have done it for the previous examples, but I'll just start to stick it in here. So the rotation here, delta 1 naught, is equal to the integral over the bending moment going through the integral of the bending moment of the beam. So the bending moment of two beams, so I won't stick 0 to 20 there, so I'll stick this one here. So hopefully you can see how all this can be done pretty fast under exam conditions. So the first one here is the real case. So that is the real case there with the real loads. And here I've got the hinge. Okay, so I'll be drawing that bending moment later on. Actually, why not just draw it now? So equals 1 over EI. And then we'll have the integral from 0 to 20 meters. So this is real, that's a hinge or a pin. So I'm just going to be drawing my 20 meters and I'm going to be at halfway. PL over 4, or 100 times 10 divided by 4, which is an equation that should be in your head anyway. I'm going to be drawing the bending moment. So obviously no bending moment on this portion. And then on the other side, I'm just going to be, just going to be sticking a hogging bending moment on, but I could equally be sticking a sagging bending moment on, and I don't really care. So this one here for the hogging, I'm going to be calling that 1 kilonewton meter bar. Okay. So I'm going to be sticking that one on, and again here that's got the hinge. So both of these are real with the hinge, and I'm solving for the case where this this change in angle compensates for this change in angle, so that it goes back to being 180 degrees. So you can see this one is going, this one is opening and this one is closing. So I should be able to calculate X such that the opening moment is the same as the closing moment, meaning that gradient, meaning that line continues straight. Okay, so that's what I'm solving for. And then here I would draw the bending moment of the hogging case. So the bending moment of the hogging case would be going up there. Okay, and then so this is virtual and this is virtual. So obviously that's 1 kilonewton meter bar since it's virtual. And then I'm going to be sticking on my dx. Okay. Okay, so that's the end of step 2, and now all that is needed is to calculate it. So 1 over EI, and then I'll go to my appendix 3 here, and I think, so obviously I can ignore that bit there. So this bit here can all be ignored because it's 0 times a value, which is going to be 0. So I'm just going to be having to do my integration from 0 to 10. So that's 10 meters over there. So I'm going to be concentrating on that shape there. So I think that shape is going to be 8. So I'll just put 8 there as that shape there. And then I think the second shape is going to be a 4. Okay, so it doesn't, so I know that the 4 one here is drawn on that side there, but you can probably see if that had been flipped to the other side, the integral, the magnitude of the integral wouldn't change. If you're not comfortable with that, don't worry, just do it either using appendix 2 or just use it through direct integration. So that you're really confident you've got the right answer. So 1 over 2, so L over 4. So this, remember that L is 4. So I'm looking at shape, it's shapes 8 and 4. So that's going to be 4, 8, because obviously 8, 4 is the same. So 8, 4 will not be shown here. Okay. Just checking the camera. So 8, 4, 4, 8. 4, 8 would be L over 4. Okay, so L over 4, and then the 4 is going to be a 4, which is going to be the biggest, which is going to be the magnitude there. So let's multiply, sorry, that's going to be the 8, so A8. So A4 is clearly going to be 1. Okay, so A4 is clearly going to be 1, or the one bar if you really want me to show it that way. The L is clearly going to be the 10 meters, so it's going to be 10 over 4 or 2.5. And the A8 is going to be PL over 4, so working out the bending moment at that point there, working out the bending moment at that point there of simply supported beam. So 50 kilonewton would be the reaction here multiplied by 5. So I'm going to make that to be 250 kilonewton meters as the real. Okay, so A8 becomes 250. And if you work all of that out, 2.5, 250, you're going to get 625 divided by EI, and I might just stick some stuff there to show that. Okay. So I'm going to get 625 over EI as my delta 1 naught. And my delta 1 naught is therefore going to be 625 divided by EI. Okay, so I'm halfway through being able to work out the value. Now let's do the delta 1 okay, so I've done the delta 1 naught, so let's do the delta 1 delta 1 put the mod sign on, is going to be equal to so delta 1 is going to be equal to 1 over EI integral of the bending moment of two shapes. So this one here is going to be the first structure with the hinge, remember, and I want to stick that one there. Okay, so remember that's the hinge, and this time here I'm going to be applying a hogging bending moment, real. So this is real. And then this time round, I'm now going to want to be working out the angle that it's rotated. So the virtual system is the same as the real system in terms of the spans, the length, the support conditions. But this time I'm at the position where I want to calculate the rotation. I'm going to be sticking 1 kilonewton meter. So I'm going to put a bar there to show it's the virtual 1 kilonewton meter. Okay, so next step is put dx, so, and then that is going to be integrated, so stick that there if I wanted to, so 1 over EI times the integral of 0 to 20 meters, so draw out the real bending moment diagram. So the real bending moment diagram is going to look something like that. And then draw out the virtual bending moment diagram, and the virtual bending moment diagram in this case is going to look the same as the real bending moment diagram. That value there is going to be 1 kilonewton meter, and then that value there is going to be 1 kilonewton meter bar. And then I'm going to be saying, well, put dx there. So lots of ways to do it. You could treat that one there and just multiply by 2, because both sides would be the same. So you could do that in your head, sort of work out half base times height of there, centro 2/3 over, read that value off. You've got the answer. You could do it using a pen. You could use it doing the you could use it doing direct integration in terms of just working out that slope, multiply the two together and do the integral. But we're just going to grab the appendix here to demonstrate it, and we're going to have two shapes. One shape is going to look like that, and the second shape is going to look like that too. And then it's going to be A8. So two shapes together, so 1 over EI and 8, 8, both shapes are the same, so look for 8, 8, that's a lucky number. L over 3 A8 squared, L over 3 A8 A8 for the first one and the second one. So the first one, the A8 belonging to the first one is clearly going to be 1, so I'll get rid of that 1. And then the second one is clearly also going to be 1, because it's the same, and the L in this case here is going to be the 20 meters, since I've chosen to use that shape 8. So get rid of that and stick 100, and if you work that out, that should be 6.66 recurring. So I'll go 6.67 over EI, since I don't like that number. And there you get your answer. So now you've worked out your delta 11, and then you've worked out your delta 10. So 625, and this is 6.67 over EI, and then cancel everything out. So you can divide the two by each other, and this is going to be a pure number with no units, and it's going to be 93.75. 93 and 3/4. So that tells you that, remember, this is the problem with the continuous beam, and we've divided it into 2 bits that we've solved separately for the rotations by putting a hinge there, and now this is by working out the x, we've restored that to not having a kink in it, and we know that the bending moment now is 93.75 kilonewton meters. So let's draw. Okay, so let's choose to draw this up here. So there was a question on Piazza about the active bending moment and the reactive. So if that's A, B, and C, let's start off with the active bending moment diagram. So the active bending moment diagram on span AB is going to look like that. Okay. And then the active bending moment of span BC, which I'll show to one side. There's no load acting on there, so the active bending moment diagram is going to be 0. So this is the active. And then we now have the reactive bending moment. So the reactant bending moment diagram. So the reactant bending moment diagram, I suppose let's just keep the 2 spans separately, because that's kind of nice, because each one's got its own free body diagram. The reactant bending moment diagram of span at A is going to be 0 because it's a pin. The active reactant bending moment diagram at B is going to be 693.75. So we've got 93.75, so I would maybe show that up there as 93.75 kilonewton meters. And of course, I'll say that one is 250. So 250, 50 times, 250 kilonewton meters as the maximum value on that one there. So this one is the reactant, going up here on the other side, and then going back down to 0. So of course you would put the dotted line there and the dotted line there. And then to combine them, you need to add them together. So you've got your active, you've got the reactant, you add them together, that's a 250 drop. So what you could do is you could say 93, so this is halfway along. 93.75 over 2 is that value there, which you can punch into your calculator, which would be hogging, and then sagging must be the other sign. So 93.75 divided by 2 minus 250 would give you that value there. And if you wanted to draw it out after adding the two together, so put an equal sign there, and you would get something that would look like 203, maybe there, then maybe some a bit further down. Okay, so we might get something that looks like that. Okay, so 0 plus 93.75 gives you 93.75. 250 sagging plus 93.75 hogging divided by 2 would give you that value there, which would be 203. 203 kilonewton meters sagging in that case there, and then that one would be 0. So every point, so this is the active plus the reactant would give you the final answer. Okay. And what would you do on the other side for the final answer? You would get adding that Benny moment to this one here, so that would be 0. That would be up there, and then this time here, because there's nothing to add it onto, put the solid line down, and that value there is also 93.75. And remember, it's hogging, so that would be this. That would be the direction of the bending moment diagram. Now, so if you now wanted to work out the reaction at A, so if we wanted to work out the reaction at A, for example, then you can just use this bit here by itself. Okay. So we've got 250 sorry, that's 100. That's 100 kilonewtons. So I probably don't want to do this for you, but it's on the answer sheets in the Dropbox. So that would be 100 kilonewton there. So just do it by yourself. You could work out the work out the shear force. You could take moments about there. So that would be 93.75 kilonewton meters. So clockwise, that was clockwise, so 93.75 plus RA times 10 meters minus 100 times 5 meters, and that would be enough for you to work out what RA is, and then you could get the reaction there by RA minus 100. You could do similar thing on the other side here to work out what the reaction at RB is. So RB must be an LRB times 10. RB times 10 must be equal to the 93.75. So then you can get RB immediately. So we can see that one's going like that. So if you did that, the RB would turn out to be negative. So I would just swap directions, and then I would put 9.375. Okay, and then I don't want to do it for you, but if you wanted to, you could work out the gradient of that line there, and then you could draw out the shear force diagram of this line here. So the shear force diagram would be of a constant gradient, and again, I don't really want to do it for you, but you could work out the gradient of that line. So you've got that point 93.75, you've got that point there, so just add the two together and divide it by the 5, and you're going to get the shear force, and then from the shear force you can add that onto the 9.375. So lots and lots and lots of ways, lots and lots of ways for you to work out the reactions. And if you can't do it, just put a message on Piazza and I'll try and I'll clarify. But it's also all written out anyway on the Dropbox solution. Okay. So I've left you a few things to think about if you've not been able to work it out for yourself. So that reaction there would be the sum of these two shear forces. Okay, so the combined solution, put it all in the same line. So go down, go up, and then go down to 0. And in one sort of step, we've been able to immediately get the reaction. We've immediately been able to get that value of 93.75. So for this type of problem, I would say that the flexibility method is a lot faster than the slope deflection method. Okay. Because you could probably punch the numbers into your calculator and get the answer out in a few minutes. Alrighty, so now let's have a look at the course notes. So statically indeterminate structures are those for which support reactions and/or internal forces cannot be determined using equilibrium. To analyze them, you can use the flexibility method, known as the force method, and the stiffness method, known as the displacement method. So remember, I'll talk about this later on, but you've got stiffness method, and stiffness is 1 over the inverse of the flexibility method. Flexibility, okay? So if you understand flexibility, you understand stiffness. And we've already seen all through your courses with Quincy and Lucas, what you've done in year 1. You've already come across many different methods to calculate a lot of different things. Unit load method here for virtual work to work out deflections. We've looked at slope deflection methods, and I think you've looked at moment area methods. So next year in year 3, Gary Raftery will be teaching you another method. He'll be teaching you moment area, which you've sort of covered before. So that's quite a neat method. So you've already done that with Quincy, and he'll also be teaching you moment distribution, which has a lot of similarity. It has a lot of similarity with the slope deflection method in terms that it uses the fixed end moments, and here we've also seen stiffness and flexibility. So you might be asking why you've been taught so many methods. If you're going to be a structural engineer, it's good to know all the different methods, and then when you have to do a hand calc, which you will have to, you can choose the most appropriate method. So no one's going to come and say you must solve this using virtual work or you must solve this using flexibility. You will just use the most appropriate method for each problem. And I'm not sure if I talked to you about it before, but when I asked my ex-boss what he did with stuff, he said he would always use the most appropriate method, and he would be changing sign conventions every 2 minutes or so, and whatever sign convention he chose probably depends on which side of the bed he woke up on. So when you get familiar with all of this stuff, you would be choosing sign conventions, overriding it, as we've done here with putting the bar sign here. So you'll be able to do calculations with the most appropriate method and by flipping sign conventions all the time. So the stiffness, so both the stiffness method and the flexibility method, so you know enough now to know both methods, and both of these methods would be, I would call them matrix methods. So when you go to industry and use computer software, most of the time it would be the stiffness method that's programmed, but the stiffness matrix is just the inverse of the flexibility matrix. So whichever way you do it, you get to the same thing. Okay. So it's good to know that computer software would be using a matrix, whether that comes from flexibility or whether that comes from stiffness. And in a lot of cases, the matrix derivations actually come from virtual work. So you can see everything's mixed up. So in this course, we will study in this section, because I want to talk about stiffness later on. In this section, we'll talk about the flexibility method. And it's general in computer applications and computer techniques. That's basically everything that I've just said. Computers use matrix methods. So, basic idea and concepts of the flexibility method. So, let me just check, as I can't remember. This one should be quite simple. So the first one is the prop cantilever. So this one here is a beam, and instead of having the point load, it's got a UDL. So I'll just quickly talk you through the solution, the support reactions. You remove the support at the end, and then there's a deflection, and that deflection is delta 1 naught. The resulting non-prop cantilever is statically determinate, which you can see here, and then here we're adding the virtual, the unit load or the virtual force down here, and that will give you that bending moment diagram there, and then you should be able to work out delta 1 naught is going to be equal to WL4 over 8EI. So go through this one here if you're not certain, if you've got any problems, but it's very, very similar to example 1, except example 1 was a point load and this one here is a UDL. So in the above figure, M naught is the bending moment diagram and M bar is the virtual. And then we go back to the same problem, and now we're applying this X that we've been talking about, X times whatever load. And again, the reaction causes the uplift. So to work out the deflection, put that down there, and we get this delta 1, 1 out of it. So those of you who can probably see what's coming, you'll probably note that we're going to start introducing a sign convention. Okay. Delta 1, 1 is called the flexibility coefficient. It quantifies how easy deflection develops when a force is applied. Its inverse is K11 and is called the stiffness coefficient. It quantifies how much resistance to deflection is developed when a force is applied. This stiffness coefficient can be understood as a generalization of the stiffness coil spring type. So note that instead of a unit force, we have a force X, and X acts in the opposite direction to the unit load. The deflection due to X is therefore negative delta 1, 1. So you can probably spot a sign convention is going to be slipped in, and it's no longer going to be the modulus of this. Modulus is fine, it's great when you're doing a simple calculation, but if you want to program something which has 20 spans, you are going to need a sign convention. However, in reality, the tip of the cantilever does not move, and the deflection is due to the external load after support removal was cancelled by the deflection. So you can see that this stuff there, delta 1 naught, is equal to X delta 1, 1. And then you can see that X is going to be equal to delta 1 naught over delta 1, 1. So long as you have applied this sign convention. From the above, we can find the value of the reaction X that satisfies the compatibility, and you suddenly get your reaction, 3WL over 8. So maybe you might like to try this yourself at home. So the above is true value of the reaction due to the original system. So this is the original system here, which is the propped. And then in this one here, we've removed each side. In practice, use superposition while constraining the bending moment diagrams, and you get the two added together and you get that one there. So just to talk about reactant bending moment diagrams and active bending moment diagrams. So to get the active bending moment diagram of that, would be WL squared over 8. And then when we get the reactant bending moment diagram, this one here would have a value up there. This one up there would have a value up there. We know that the reactant bending moment there is going to be 0. So this one is your reactant. And this one here is the active. So the active being the simply supported beam and the reactant being the bending moments at the supports with a dotted line. I know I've drawn a solid line. Just make it a dotted line. With a dotted line drawn between them, you add the two together and you get your final bending moment shape. So because we do not have a partial shear force diagram, we will construct it using the previously found reactions and you will get the shear force diagram. So this is just one step a bit more complicated than what we did for example 1. But it introduces the idea that we're applying the unit load, we're getting rid of the modular sign and we're applying the unit force in the direction downwards so that you can write this out with a negative sign, bring that to the other side so there's no negative and divide the two by each other and you've got your x. So degrees of statical indeterminacy. So the flexibility method requires a changing statically indeterminate structure achieved by removing supports and releases. So we've talked about all that before. At this stage here, if I can find it. So some students like having a formula to help them determine whether something is statically indeterminate by how much. I think if you use a formula you can get confused, so it's much easier just to understand what you're doing. So you can look at that and say if that support disappeared, it's statically determinate. This support adds 3 reactions, therefore statically indeterminate by 3. This one here, pin, pin, so this one is statically determinate. But that one's not a roller, so it's not quite the same as that. So this would be statically indeterminate by 1, because this one here is fixed. If these two disappeared, then it would be statically determinate. So 3 reactions, statically indeterminate by 6. And then this one here, if that one and that one were there, it would be statically determinate, but you've got this one here and this one here, both with a vertical reaction. So this one is statically indeterminate by 2. Okay, so try not to be guided by an equation, just look at it because the equations can sometimes mess you up. So, degree of statical indeterminacy, we covered there. So we restrict our attention to straight beams with planar loads at 90 degrees. And then we come to example number 6. Okay. So find the support reaction, shear force diagram and bending moment diagram for the continuous beam shown below. The beam has a uniform bending stiffness of EI. So what you could do is you could delete that, work this out here. So for the reactions, which I don't really want to go through. Okay, so you could do that, but there is a preferred solution, and the preferred solution is what we've been describing here by making that into a pin. Sorry, by making that into a hinge, so that you've got your simply supported beams on either side. So the bending moment diagram produced by the external loads. So M0 will probably stand for the external loads. I'll just turn the light on. When I hit the age of 43, the optician told me, you've hit 43, your eyesight's going to go. And I said, how can that be so accurate? And they were right. And then when my wife hit 43, same thing happened to her. So it does become a bit hard to see when you get old at the age of 43. So the index is such that delta 1 naught is the first index corresponding to the location of the displacement, i.e. the ith displacement, and the second index to cause that of displacement rotation. So the second index is reserved of 0, is observed for external loads. So delta 1 naught, this one here is for external loads. And delta 1 1 is not the external load. So remember, when you go back to this one here to get the 1 naught, we are calculating something based on external loads. And this one here with the index of 1, it's not external loads. So this one is 100, the 100 doesn't appear here. So that one would satisfy not external loads. Okay, so hope not external loads. And the second index to cause that displacement rotation. Okay, so the index convention is such that delta 1 naught, the first index I corresponds to the location of the displacement. So 1 stands for which release. And this one stands for which release. So in this problem here, we only have one release. So there's only one release, okay? But if we had a 2-span, not 2-span, a 3-span beam, and contrast that to what we've already solved, which that one there. So this one has one release, so make one release there, and this one has 2 releases. And if there were 3 internal supports, there would be 3 releases. So everything we've done up to now has had 1, okay? Everything we've done up to now has had 1 because there's only 1 release. But if you wanted to set up your matrix, there will be more than 1 release. So first one tells you which release, and second one tells you whether external loads 0 or not external loads. So the bending moment diagram M naught, when naught is produced by the external loads in the statically determinate system, is shown here. So we can see we've got your beam, we've got the load, and here. Okay. So at this stage here, you can see a sign convention coming in. So the sign convention seems, in this textbook, seems to be sagging is negative. But as I said, with bending moments, plot on the tension side, and you can decide whatever sign convention you want, and as long as you're clear in your head, you're not going to get lost. So the bending moment diagrams produced by the pair of unit moments at the newly introduced hinges are as follows. So one hinge there, so 2 hinges. So we put a hinge there, we put a hinge there, hinge there, hinge there. So this is the new problem to calculate the reactant bending moment. And you can see that they're always shoving it in the sagging direction. And the reason why they're always, so when I was doing it, I didn't really care. Okay, I was putting it 1 second, I might be putting it up, next second I might be putting it down. But you got to be careful when you're writing a computer program, okay? So in this case, sagging is, you always are putting a sagging. And it's just a convention. The author of the textbook or the computer program could have adopted the other way, but they're doing it this way so that when they bring that to the other side, you don't have a negative sign. So, applying sagging. So applying sagging here. So you go to each release in turn and you apply your bending moment at that point there. So this one here, that release is going to lead to that bending moment, and that's not transmitted to here because that's a hinge. And then similarly here, this one here, you apply there and it's not transmitted to this span here because that's a hinge or a pin. Cool. So the relative rotations produced by the external loads delta 1 naught and delta 2 naught. So 1 stands for first release and 2 stands for second release. and we can see it's going over all members, and it just considers these two, and the 2 naught considers these two here, and there's no need to drag this bit here or this bit here in, because bending moment here is 0 and bending moment here is also equal to 0. So you do that, and then you get your delta 1 naught, which we had here for the 1 release with the real loads, and then here you get your delta 2 naught, which is your real loads at the 2nd release. So the relative rotations going through each of the releases in turn, and you can go up to 10 releases or 100 releases in turn. And then we're now able to calculate the relative rotations. So we're now onto your delta 1 1 and your delta 2 2. So second notation, this one would be first release, this would be second release, and that one would be which external load set you're applying to. So you're going through each one in turn. However, the unit moment pair applied at x1 also causes deflection at x2, denoted by delta 1 2, and vice versa, because if you apply a load there, there will be a deflection. So this one here causes a deflection on the rest of the beam. So there is a knock-on effect. So it causes, so the moment pair release applied at x2 also causes deflection at x1, denoted by delta 1 2, and vice versa, denoted by 2 1, and these two deflection pairs are evident by calculating them. So you can work out the entire component of the matrix. So the table below summarizes these coefficients. So when we had 1 release, remember, we only had delta 1 naught and delta 1 1 to worry about. But when we've got 2 releases, we've got an additional number of 3 to worry about. And then here they've tabulated the coefficient of each member, which you can see here. And if you're wondering what's happening here when they do the summation of these, it's to work out the bending moment diagram, the reactant plus the active. Okay, so that's how it can be shown in a tabulated form. So returning to the original study, statically indeterminate system, we noticed that under the combined action of external loads, x1 and x2, both relative rotations must be 0. So we've got these two equations, and we can see that we've got a matrix form. So we've got your x's, and we've got our deflections, and then these are the flexibility components: delta 1 1, delta 1 2, delta 2 1, and delta 2 2. And before, when we had one system, we only had delta 1 1 x is equal to delta 1 2. So hopefully you can just imagine how the matrix has now become 4 terms. So we have the flexibility matrix, which would be the delta 1 1, delta 1 2, delta 2 1, delta 2 2. We've got some matrix there ready for inversion. The vector of the redundant forces x1 and the vectors of the displacements 1 0 and 2 1. So using the above notation, x delta f, you can invert. So we did say it's a matrix, so you can invert it to find the stiffness, and then the inverse of the flexibility matrix is the stiffness, because stiffness and flexibility are inverses of each other. So return now to complete our example. We can put these two in here for the x1, x2. X1, x2, take out this, you've got a matrix to invert that matrix, which you will get here, and you can suddenly solve for the x's, which is the vector of unknown forces, or the bending moments. And then we would have our reactant bending moments, which would be these values here, these values there, that value there. So the reactant, of course, is just at the support, and you'll be adding that onto the active bending moment in each of the spans, and then you'll be able to pull out the values of the bending moments at whichever position you want within each span. So reactions and shear forces can be found from the bending moment diagram and external loads by considering equilibrium corresponding to each span. So of course, I don't think it would be. I don't think I've ever given more than a 2-span question for the flexibility method in the exams. So what we'll do here now is to go through the notes that I've written out. So the previous examples, being 1-span or 2-span, did not require a sign convention, as it was obvious which direction the vertical reaction or the bending moment would be at the end of the calculations. The flexibility equation was therefore expressed as delta 1 naught over x, delta 1 naught over delta 1 1, meaning that we do not need to worry about a sign convention. Let us now adopt a sign convention consistent with this course book in this section of sagging is positive and hogging is negative. For a 2-span beam, therefore, delta 1 naught minus x delta 1 1 is equal to 0, which is one equation. And for a 3-span beam, delta 1 naught minus x1, x2, x1, x2 with the coefficients here has got 2 equations. And hopefully by staring at that one, you can see that you're going to get a 2x2 matrix from a 3-span beam. And for a 4-span beam, you're going to get a 3x3 matrix, and so on. And the point is, this can be programmed. Okay, that's the main point to take out. So, example of 2-span beam with point load using method consistent with course book. Okay. So, I'm going to go through. I'm just going to talk you through this one. Just to put it in the same format as the course book with the sign convention. So, and this, if you've not noticed, is the same as this problem. Okay, so it's the same problem, and now the second method is doing it consistent with the course book. So that you can see how it can lead to a calculation, to a computer program. So span ABC continuous there is equal to putting a hinge there. So we've got that one, that portion there, and that portion there, since there's a hinge there. And then you've got x times 1 kilonewton meter. And remembering in the course book, they always put it as sagging. Which is great, because if you've got a 3-span beam there, then you know you don't even need to think. You're just going to be sticking a sagging bending moment on each of the internal spans one by one. Okay, so without thinking, you could just put a sagging bending moment according to the sign convention. So for span 1 1, this is member AB. This would be the shape of the bending moment diagram, which you can see there. Okay, so you can see that there. And then for delta 1 1, which is the other one, you would have that as the bending moment diagram. So we're now working out the position of g of x. So you can see this is programmable. Because you would be using the graphical method. So the graphical method requires the area of each one plus the centroid. So you can see you can tabulate all of these. So I know this is just 2 spans, but you can probably imagine if there was 20 spans, you could see how everything could be tabulated. Find the centroid, find the position, do it for each of the members there, and then stick that into a table that I've drawn out for each of the members, for each of the terms, and then sum the two together and you will get the flexibility coefficients, consistent with the sign convention adopted in the course book and in the tabular form that you can see can be used for programming. Delta 10 minus x delta 11, and that will give you your 93.7. And then again, you could probably imagine that being in the spreadsheet, where these positions here are the locations within the span A, B, and BC, and then all 0 here for the real case there, and then these coefficients put here, and then the numbers coming out here. So obviously that is the reactant, and then this would be the active plus the active bending moment plus the reactant bending moment to pull out these things consistent with positive sagging and negative hogging. And then you can see from there that you can pick out each of these points coming 0, 0, that one, that one, that one, that one, that one, that one, and then that one there. Get the bending moment diagram. From the bending moment diagram, you could probably see that a computer program could turn that into the shear force diagram just by looking at the loads, working it out. And then from there, you would be able to see that that reaction there would be the shear force diagram of that one at the end, plus the shear force diagram of that one to give 68.8 kilonewtons. So what we've done, I've gone through my own examples, basically reinforcing that you don't need to worry about a sign convention, and then we've talked about how a sign convention could be set up and how something could be tabulated for more spans. Okay. So next time, so we've talked about beams, and next time for static, so everything we've done so far, I suppose you could have done anyway using slope deflection, but next time we'll start talking about flexibility method and the analysis of statically indeterminate trusses, and there will be a few examples that you can go through for the trusses. So if you wanted to, you could have a look at the pre-prepared solutions anyway for the truss problems. Okay. So that's what's coming up next, and after that I'll give you a chat about stiffness.